All right, here we are in chapter 8 for pre-calc, and we are going to be looking today at sequences and series. So here we have just an introduction into sequences and series, and then later on in the chapter, we're going to look more specifically at specific types of sequences and series called arithmetic and geometric, and also look at finite sequences and series, as well as infinite sequences and series. All right, so I would like you guys to start by pausing the video and doing these first 4 warm-up problems, letters A, B, C, and D. And remember, you can print the file that I'm working on right now from the files folder in the team. So go ahead and do that, pause the video and work on these problems, and then return. All right, so let's see how you did on these first 4 questions. So a sequence is just a list of numbers. And so here we're just looking at this list of numbers and we're looking for a pattern. So we can identify the pattern here. And what you should have found for the pattern, that the next 3 terms are going to be 64 over 720. And then the next one is 128 over 5,040. And then the last one is 256 over 40,320. All right. So maybe it's not the easiest pattern to find. Some patterns are going to be easier. Some patterns are going to be harder. Some people are better at recognizing patterns than others. Okay, so things that you want to think about. Are you adding from one term to the next? Are you multiplying? Are you dividing? Are you multiplying by the previous term? Are you doing any powers? Is it, powers of 2, which in this case we have powers of 2 in the numerator, powers of 3, powers of 4. We also have something called factorials. Factorials you're going to see a lot as well. And so a factorial, if you're not sure what that is, if you have 4 factorial, that exclamation point means factorial, then that means 4 times 3 times 2 times 1. So you multiply all of the values all the way down to 1. All right, and 4 factorial is in fact going to be 24. I'm just going to put equals here, 24. If I reverse 3 factorial, would just be then 3 times 2 times 1, which that is equal to 6. 5 factorial would be 5 times 4 times 3 times 2 times 1, which is 120. And you can see that those numbers are here at the denominators. Okay, so you're going to see factorials as well a lot in these patterns that we're working with in this chapter. All right, so describe how the pattern relates to the term before it. Well, what we can see is if we take the term before the previous term and we multiply that previous term times 2 over n minus 1, then we will get the next term. So to write that out using certain proper notation, we say a sub n is the nth term, is equal to the term before it, which is a sub n minus 1, multiplied by 2 over n minus 1. So a sub n here, this represents the value of the nth term. And this here represents the value of the n minus 1 term, which is the term that's before the nth term. So you want to familiarize yourself with this notation if you're not familiar with it already, but you should have seen it last year in Algebra 2, and you should be familiar with it. Now, this type of formula here, type of formula is called a recursive formula. Okay, because it relates to the term before it. A recursive formula is dependent on the terms before, or maybe it's dependent on 2 terms before. Sometimes we see patterns where you add the 2 previous terms and you get the next one, or you multiply the 2 previous terms and you get the next one. Okay, so anything that depends on something that, anything that depends on a term before it is called a recursive formula. We have another formula that's called an explicit formula. And so if I ask you to do something like in part C, I ask you to find the 100th term, you don't want to have to use the recursive formula because a sub 100 would be a sub 100 minus 1 times 2 over 100 minus 1. Well, that means in order to find the answer to this, you would need to know what the 99th term was. Well, in order to get the 99th term, you'd have to know the 98th term. And in order to get the 98th term, you'd have to know the 97th term, and so on. Okay? But if you recognize that the numerators are powers of 2, so these numerators here are powers of 2, and the denominators we saw were factorials, you can relate those back to the value of n, and then you can find the 100th term directly. So a sub 100 is going to be 2 to the 99th power over 99 factorial. And you don't have to actually calculate that numerically, but that's perfectly fine for that answer. And how did we find that? We found that by using what we call the explicit formula. And so the explicit formula would be a sub n is equal to, we take 2 to the n minus 1 power. So for the first term, it would be 2 to the 0. For the second term, it would be 2 to the first. For the third term, it would be 2 squared, and so on, divided by the quantity of n minus 1 factorial. Okay? And again, this is just pattern recognition. So take some time to go back and look at that pattern and see if you can see what I just explained about that pattern, and make sure that everything makes sense to you. And the more you work with patterns, the easier they will be to recognize. Okay, so you'll get better at recognizing patterns the more you work with them. All right, so let's move on to some definitions. So here we have some vocabulary. So the vocabulary that we have here, first of all, a sequence. A sequence is simply just an ordered list of numbers. Okay, so it's just a list. It's separated by commas. So really important there. We just separate it by commas. And then we have two different types of sequences. We have finite and then we have infinite. So a finite sequence means that it ends. It contains a finite number of terms. So here we have 1, 2, 3, 4, 5 terms. Okay, so a total of 5 terms. And then we have what we call an infinite sequence. An infinite sequence has an infinite number of terms. So you can see on the end here, we have the dot, dot, dot. That means infinite number of terms, right? It keeps going and going and going forever. Okay. All right. I just talked about recursive formulas as well as explicit formulas. Okay. But just to review, you can see the formal definitions here. And I did notice a typo right here in this spot right here. This should say not a sub 1. That should say a sub n minus 1. Okay, so we're saying that the nth term here, a sub n, let's use a different color, a sub n is equal to the previous term, a sub n minus 1 plus 2. So we're adding 2 to the previous term. So here, if a sub 1 is 3, then the next term I add 2 and I get 5. The next term I add 2 and I get 7, and so on. Okay, whenever you have a recursive formula, you must define a starting term. Okay, so recursive formula kind of has a minimum of 2 parts to it. So here you must define a minimum of 1 term. So we have a sub n defined as well as a sub 1. For an explicit formula, or this can also be called the apparent term or the apparent formula. This gives the nth term just as a function of n. So that means you could find the 1 millionth term just by just plugging in the number 1 million. So here, if I wanted you to find the 100th term, a sub 100, then that would just be 2 times 100 plus 1. Okay, so it'd be really easy to find. Over on the left, for the recursive, if I wanted you to find a sub 100, you would have a sub 99 plus 2. So you'd have to go and reverse that and go, oh, well, what's the 99th term? And then what was the 98th term, and so on. Okay, so hopefully you can recognize the differences between those two different types of sequences. Okay, so now a little more practice. Go ahead and try these. Okay, see what you remember about factorials. as well as just expanding now that we just talked about and reviewed some of that vocabulary. So go ahead and pause the video and try these 4 problems, and then restart the videos to get the answers. Okay. All right, so for the first one, when you're writing the first 5 terms of this sequence, we have a sub 1 is 15. Okay, so there's our first term. All right, so we have 15. The second term now. So if I plug in for the second term, that means that my k is going to equal 2. So for k equals 2, then what we have is we have a sub 2, which is a sub 1 plus 1, is going to equal a sub 1 plus 3. Okay, and so that means I take the first term, a sub 1, which is 15, plus 3, and that gives me 18. So, sorry, this is for k equals 1. Okay, but that's going to give us our a sub 2. So our second number is going to be 18. And then for our third number, we would do k equals 2. K equals 2 is going to give us a sub 2 plus 1, which is a sub 3. And so then we have is equal to a sub 2 plus 3. So a sub 2 was 18, so we're going to add 3. So we get 21. So our third term is 21. We can see that each time we're just adding 3 to the next term. So then our fourth term is going to be 24, and our last term is going to be 27. Okay? And there's our first 5 terms of the sequence. All right, number 2, we want to find a sub 16 given this information here. So this here is an explicit formula, so we can just go ahead and plug in the 16. So we get a sub 16 equals -1 to the 16 minus 1, 16 times the quantity of 16 minus 1, and then we simply go ahead and calculate, and we get -240. Number 3, we are expanding our exponents. We're expanding our factorials here. So by expanding the factorials, as we talked about earlier, we're going to multiply by every single number all the way down to 1. But I'm not going to expand all the way because I know my numerator can cancel with my denominator. So I'm going to take 10. I'm going to start multiplying down all the way 9, 8, 7 until I get to 6. Because then 6 would go 6, 5, 4, 3, 2, 1. But instead of writing that out, I'm just going to finish that off with 6 factorial. Because I still have this 6 factorial in my denominator. So my denominator is going to have a 6 factorial in it already. So those can cancel. And then I'm going to keep my 3 factorial from the numerator just as 3 factorial. I'm going to expand my 4 down to 4 times 3 factorial. And then the 3 factorials will cancel. So I can cancel my 3 factorials, cancel my 6 factorials, and now I just need to multiply what's remaining. I can reduce my 4 with my 8 and make my 8 a 2, and my 4 becomes a 1. And when I multiply that out, then I end up with 1,260. Okay, so I want you guys to show the canceling on that if I tell you not to use a calculator. So you're always going to show the canceling, and then you can use the calculator to calculate just the multiplication, but show me that you understand how to cancel or how to expand the factorials and then cancel. All right, number 4, here we have variables. So you want to think about which one's greater, n plus 2 or n minus 1. So n plus 2 is greater. So you're going to expand the bigger number down to the smaller number. So this here is going to equal n plus 2 is my first number. 1 less than n plus 2 would be n plus 1. 1 less than n plus 1 is n. 1 less than n is n minus 1. And I would keep going, but I'm going to put factorial on the end of that because my denominator has the n minus 1 factorial. So that means I can cancel my n minus 1 factorials. And then I have n plus 2 times the quantity of n plus 1 times n. And if I multiply and expand that out, I end up with n cubed plus 3n squared plus 2n. And there's my answer for number 4. Okay. All right, a little bit more vocabulary, and then we're going to get into a few more examples where we're going to use our calculators and learn how to do this on our calculator. So here we have convergent sequences and we have divergent sequences. So convergent sequences are sequences that are going to have a limit. So we've talked about limits in different contexts in this class already. We're going to officially learn limits and how to work with them in chapter 11. Okay, but a convergent sequence means that the terms of the sequence are going to approach a unique number. So it's going to eventually converge and stop at one value. Whereas a divergent sequence will not approach a unique number, and it's going to continue getting bigger, 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 or smaller, 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 smaller. Okay, so it's going to continue to grow to either positive or negative infinity. Then we have a series. A series is an indicated sum of all of the terms of a sequence. So sum here means that we're going to be adding up all the terms of a sequence. We have a finite series and we have infinite series. So a finite series is the sum of all the terms of the finite sequence. Infinite series is going to be the sum of all the terms of the infinite sequence, which seems kind of weird that we can add up all terms to infinity, but we'll learn how to do that in the future. Then we have a partial sum. A partial sum is just the sum of the first n terms of a sequence. So you're just looking at a certain number of terms, but not the entire series. All right, then we have summation notation. So summation notation, you guys should remember from last year. So we write summation notation using this here, which is called sigma. So sometimes you'll see it called find the sigma notation. And what that means is you're going to add up all the numbers by first plugging in this bottom number of 1, and then plug in every number up to the top number of n. Okay, so the bottom number is the first number you plug in, first number to plug in. This top number, the n, is the last number to plug in. Okay, and you add up all of the terms for every single number in between. Now, you're going to be asked to write explicit formulas. So this formula that you put inside here, when you're writing a summation notation, this is always the explicit formula. It is never, 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 never the recursive formula. Okay? All right. Oh, and this little I value is called the index. So that's the vocabulary word for that. That's the index. And you have the lower limit and you have the upper limit. Okay. All right, so that's sigma notation. So let's look at an example of sigma notation for number 1, and then we're going to see this on our calculator as well. So it says to use sigma notation to write the sum, and then we'll use our graphing calculator to actually find the sum. Okay, so to use sigma notation to write the sum, if I look first here, you can see it's kind of grouped into sections. We have this first group plus the second plus the third plus the fourth, and we can see that things stay the same. So in every single part, we have a 1, then we have minus, 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 and then we have a denominator of 6. And then we have that quantity is going to be squared. So all those things in blue stay constant. The only thing that's going to change is that numerator. So I'm looking at the numerator, I have a 1, then a 2, then a 3, and then up to a 6. So this term, this first one here, this is called the first term, so that's when n equals 1. This is when n equals 2, and so on. When n equals 3, this one here then is going to be when n equals 6. So writing in our sigma notation, we're going to put sigma. We're going to start off with I equals 1, and we're going to end at 6. We have the quantity of 1 minus a fraction with a 6 in the denominator to the second power. The numerator of that is what changes, so I'm going to put that as my I, because it goes from a 1, and then a 2, and a 3, and a 4, and a 5, all the way up to 6. Okay, so there we have our sigma notation. Okay, so on your calculator, guys, you want to learn how to utilize your calculator to do this, and you have a summation notation on your calculator. So you can see here, I took pictures of the calculator screen, so you can follow along with that. Okay, and so to get to this here, you are going to press the math key on your calculator. Okay, and on the math key, you're going to arrow all the way down to option number 0, which is after the 9, right? It's like all the way down. So you're just pressing the math key. The math key is the third one down on the left side underneath the alpha key on your calculator. Okay? And then you are going to choose summation right here. So choose option 0 for summation. And when you choose option 0 for summation, it's going to give you, if you have an older calculator, you're going to have to kind of type in what's on your screen. Okay, and if you have an older TI 83 or 84 and you're not sure how to figure it out, let me know. But otherwise, you're going to see this here on your calculator, but it's going to have boxes, missing blanks for all of these things here. And you're just going to type in the lower limit, the upper limit, and then you're going to type in the formula. So when you go ahead and type all that in, and when you press enter, you're going to see this answer here of 3.472222. And I'm usually going to ask you for that as a fraction. So you want to make sure you know how to change it to a fraction. So to change to a fraction here, you just press the math key and then the math key option number 1. So to change it to a fraction, that's just the math key and then it's option number 1. And it changes to a fraction and you get your answer of 125 over 36. All right. Example number 2. We want to find the fourth partial sum and the sum of the infinite series. Okay, so the fourth partial sum means we're going to add up the first 4 values. So we can just do this in our heads. We don't need our calculator for this one. So the first 4 values would mean I'm going to first plug in a 1. So I'm going to take a 1 and I'm going to plug it in. Oops, not there. I'm going to plug it in for the exponent. So that means I just have 2 times 1/10 to the first power. Okay. And then I'm going to add that 2. So then it's plus, and then I find the second one. So then I plug in a 2 for that exponent. So 2 times 1/10 to the second power, plus then 2 times 1/10 to the third power, and 2 times 1/10 to the fourth power. All right. So if I calculate this then, here I have 2/10 plus, then I have 2 100ths, and then 2 thousandths, and 2 10,000ths. If I change those to decimals, we have 0.2 plus 0.02 plus 0.002 plus 0.0002. So that means that that here is then equal to, my equal sign in there, is equal to 0.2222. Wow, that's interesting. Okay. And that's going to be my fourth partial sum. So the sum of the first 4 values. Now, if I want to find the infinite series, so what if now this went all the way to infinity? I kept adding more numbers. Well, look at what the pattern that we had. We had 0.2 plus 0.02 plus 0.002 plus 0.0002 plus and so on. Whoops. And so we keep on adding another place value with a 2. So what that's going to end up being is 0.2222222222222 repeating. Remember that repeating bar over the top? And if you remember, if you know how to change that into a fraction, that's going to equal 2/9. And if you don't know how to change it to a fraction, we will learn that later this chapter. Cool. All right. One more example, and we're going to be mostly using our calculator for this one, and then a little bit of analysis after we use the calculator. Okay. You guys should hopefully remember this from last year from Algebra 2. And so we're just kind of expanding on what we're doing, what you guys know from Algebra 2 already. So we're using our graphing calculator to write the first 5 terms of this sequence. And then it says find the first 5 partial sums. So S sub 1, S sub 2, and so on. Okay, so to find the first 5 terms of the sequence, what we need to do is we need to use our calculator. And now I'm forgetting where we go on our calculator. All right, so we are going to go into our sequence menu, which is, all right, so second, and then press the stat key. So to get here, we're gonna do second, okay, so press the second key, and then press the stat key, okay? So second stat, and above the word stat is the word list, okay? So it's kind of next to the left arrow on your calculator. So second stat, then you're going to arrow over until you get, so arrow over 1 so that you're going to the ops menu. And then we're going to choose option 5, which is sequence. Okay, so we choose option 5, which is sequence, and then your calculator is going to give you this menu. So it asks you to input the expression, the variable, the starting point, the ending point, what you want to count by. So we're counting by ones. Okay. And then once you get that all done, you're going to keep arrowing down until you're highlighting on paste, and you press paste. Okay. Now, if you have an older calculator, okay, so this one is if you have like an 84 or an 84 plus. Okay. If you have an older one, like you have the TI-83s, the TI-83 is simply going to write this sequence parenthesis on your screen. Okay, so what you need to do then is you need to type this stuff in the right order on your own. So if you have the older calculator here, the TI-83, you're just going to go from the first one all the way to the second. And the order that you type it in is you type in the equation. So you're going to get to the sequence. Then you're going to type in the equation. And then you type in the variable. And then you type in the lower number. And then you type in the upper number. And then you type in what you want to count by, which is usually what, for our class, we're always going to count by ones. Okay. And then you put commas in between all those, and then you press enter. And then you should get the same list. Now, notice when you get this list here, this list is in decimals. So we want to change it here into fractions. Okay. So what that means is that this first number here is my a sub 1. This second number is my a sub 2. This is my a sub 3. This is my a sub 4. And here we have my a sub 5. Okay. So we found the list of the first 5 terms of the sequence. The second part of the question here asks us to find the first 5 partial sums. So we're finding s sub 1, s sub 2, s sub 3, and so on. So what that means is we're going to add up the terms. So s sub 1 is simply equal to the first term. So that's a sub 1. So that's just 1/2. So s sub 1 is just 1/2. Okay. S sub 2 is going to be the sum of the first 2 terms. So it's a sub 1 plus a sub 2, which would be 1/2 plus 1/6. We add that together and we get 2/3. And then s sub 3. So s sub 3 is a sub 1 plus a sub 2 plus a sub 3. We can also think of s sub 3 as s sub 2 plus the a sub 3, so that we don't have to add so many separate terms. So I can think about it as the previous one, 2/3, plus the a sub 3, which is 1/12, and that's going to equal 3/4. Okay, so s sub 4. You don't have to write it all these different ways, but I just want to give you guys options for how to think about it. So s sub 4 is going to be s sub 3 plus a sub 4. So it's 3/4 plus 1/20. And when I add that, then I get 4/5. And maybe you see the pattern happening already. S sub 5 is going to be s sub 4 plus a sub 5. So it's 4/5 plus 1/30, which is equal to s sub 5 then is 5/6. The last thing it asks us to do is says, find an expression for this partial sum. So if I kept going, what would be S sub n? Well, what I can see here, this 2 matches the 2. The 1 matches the numerator. 3 matches the numerator. 4 matches the numerator. 5 matches the numerator. So that means that my numerator is going to be simply n. N. Look at the denominator. How does the denominator relate to the subscript? What you should see, the denominator is 1 more than the subscript. So my denominator is just going to be n plus 1. And there we have our expression for S sub n. All right, there's a little bit about sequences and series, mostly focusing on making sure you know how to use the calculator. Otherwise, the basics of the sequences and series you should have learned last year in Algebra 2, hopefully, and we're just expanding and refreshing that memory. All right, that's it for 8.1. I will see you next time.